Ladies and gentlemen, what if I told you that the future of electric vehicles doesn't just depend on bigger batteries or faster charging, but on something you've probably never even thought about? Imagine driving through freezing temperatures without watching your range disappear. Imagine a system so intelligent it captures wasted heat, recycles energy in real time, and silently protects the heart of the vehicle, the battery. This isn't just climate control. This is engineering that changes everything. And once you understand how Tesla's heat pump works, you'll never look at electric vehicles the same way again. And why Tesla's heat pump is essential for our future. And the future of sustainable transportation is not built on a single breakthrough. It is built on thousands of intelligent decisions working together as one system. Among these innovations, Tesla's heat pump stands out as a quiet revolution. An engineering solution that transforms efficiency, extends range, and redefines what electric vehicles can achieve in real-world conditions. And in traditional internal combustion vehicles, waste heat from the engine is abundant. Heating the cabin in winter costs virtually nothing, because the engine naturally generates excess thermal energy. Electric vehicles operate differently. Without a combustion engine producing waste heat, cabin heating must be generated deliberately, and inefficient heating can significantly reduce driving range. This is where Tesla's heat pump becomes essential. And a heat pump is not just a heater. It is a highly efficient thermal management system that moves heat, rather than creating it from scratch. Instead of consuming large amounts of energy to generate warmth, Tesla's system transfers heat from one area to another, even extracting usable warmth from cold outside air. This process dramatically reduces the energy required to maintain cabin comfort and battery temperature, especially in cold climates. And efficiency is the foundation of sustainable progress. Every kilowatt-hour saved is additional range delivered to the driver. Every improvement in thermal management reduces strain on the battery. Tesla's heat pump allows vehicles like the Tesla Model Y and Tesla Model 3 to maintain higher efficiency during winter months compared to conventional resistance-based heating systems. In real-world conditions, this means drivers experience less range loss in cold weather, an issue that historically challenged electric vehicle adoption. But the impact goes beyond comfort and range. Battery performance is deeply connected to temperature. Lithium-ion batteries operate best within an optimal thermal window. Too cold and efficiency drops. Too hot and long-term durability can be compromised. Tesla's integrated heat pump works in harmony with the vehicle's thermal architecture to regulate battery temperature intelligently. It captures and redistributes waste heat from power electronics motors and the cabin, creating a unified thermal loop that maximizes overall system efficiency. And this is system-level engineering at its finest. Rather than treating heating, cooling, and battery management as separate functions, Tesla designs them as interconnected components of one optimized ecosystem. The result is fewer energy losses, improved charging performance in colder conditions, and greater long-term battery health. And the heat pump also plays a crucial role in fast charging. When a vehicle approaches a supercharger, thermal conditioning prepares the battery to receive high power efficiently. By intelligently managing temperature through the heat pump system, charging speeds remain consistent and effective, even when external temperatures drop. This ensures reliability and convenience, two factors essential for accelerating global adoption of electric mobility. And scaling sustainable transport requires solutions that work across diverse climates. From freezing winters in northern regions to variable temperatures in urban centers, Tesla vehicles must deliver predictable performance. The heat pump makes electric driving practical in places where extreme cold once posed a barrier. By reducing winter range loss, it removes uncertainty and builds confidence among drivers transitioning away from fossil fuels. And the innovation reflects Tesla's broader philosophy: solve problems through engineering precision and integration. A component like a heat pump might seem small compared to battery packs or autonomous systems, but its influence is profound. It reduces energy consumption, enhances user experience, and supports the larger mission of accelerating the world's transition to sustainable energy. And in a world moving toward electrification, efficiency is everything. As grids become cleaner and renewable energy expands, maximizing how effectively energy is used becomes just as important as how it is generated. Tesla's heat pump contributes directly to this efficiency equation. By lowering energy demand for heating, it ensures that more stored energy is used for movement rather than waste. And the future demands vehicles that are intelligent, adaptable, and optimized down to the smallest detail. Tesla's heat pump is a perfect example of how thoughtful engineering can unlock meaningful gains without increasing complexity for the user. Drivers simply experience better range, faster charging in cold conditions, and consistent comfort, while the technology works seamlessly in the background. And this is not just about climate control. It is about redefining what efficiency means in the electric era. It is about ensuring that every advancement, no matter how subtle, contributes to a larger transformation. Tesla's heat pump represents the kind of innovation that pushes the entire industry forward, proving that the path to a sustainable future is built on relentless optimization and uncompromising engineering excellence. And it demonstrates that progress does not always arrive as something loud or visually dramatic. Sometimes it is embedded deep within the architecture of a vehicle, engineered with such precision that most drivers never even think about it. Yet the benefits are felt every single day. When stepping into a Tesla on a freezing morning and experiencing immediate warmth without watching range drop dramatically, that seamless experience is the result of advanced thermal intelligence working quietly beneath the surface. And Tesla's heat pump is built around a multi-source thermal system that captures energy wherever it exists. Waste heat from the drive unit, the inverter, and even the battery itself can be redirected and reused. Instead of allowing that thermal energy to dissipate into the environment, the system harvests it. This circular approach to energy management reflects a broader philosophy. Nothing valuable should be wasted. Every joule matters. And traditional electric vehicles that rely solely on resistive heating convert electrical energy directly into heat. While simple, that process is inherently inefficient. A heat pump, by contrast, can move multiple units of heat energy for every unit of electrical energy consumed. That efficiency multiplier becomes increasingly important as the industry scales. When millions of vehicles operate globally, small efficiency gains translate into massive reductions in overall energy demand. And this matters not only for drivers but for the power grid itself. As electrification expands, grid capacity must support transportation, homes, and industry simultaneously. Vehicles designed to use energy more intelligently reduce strain on infrastructure. Tesla's heat pump helps ensure that electric mobility grows sustainably, minimizing peak demand during extreme weather, when heating needs are highest. And the engineering challenge was significant. Designing a heat pump system that performs reliably in sub-zero temperatures requires innovation beyond conventional HVAC solutions. Tesla developed a compact, automotive-optimized design capable of operating in harsh climates. By refining refrigerant flow valve control and thermal routing, the system remains effective even when ambient temperatures drop dramatically. And in extreme cold, extracting heat from outside air becomes more difficult. Tesla addressed this by integrating advanced control software that dynamically adjusts thermal strategies in real time. Sensors constantly monitor battery temperature, cabin conditions, motor heat output, and external climate data. The vehicle's onboard intelligence determines the most efficient path for heat transfer at any given moment. This blend of hardware and software integration defines modern electric vehicle engineering. And another advantage emerges in energy recovery during everyday driving. High-performance acceleration generates heat within the powertrain. Rather than allowing that heat to dissipate and use, the system captures and redistributes it. During highway travel, when aerodynamic efficiency becomes critical, the heat pump continues optimizing cabin and battery conditions with minimal additional draw from the battery pack. And the ripple effects extend into overall vehicle design. Because the heat pump reduces winter range loss, Tesla can optimize battery size more effectively. Higher efficiency means fewer compromises between performance, range, and cost. This supports the mission of making electric vehicles more accessible without sacrificing capability. And in colder regions, one of the primary concerns for potential EV buyers has historically been winter reliability. Questions about range reduction and slow charging created hesitation. Tesla's thermal management advancements directly address those concerns. Drivers in northern climates experience predictable performance and improved confidence. That trust is essential for widespread adoption. And the impact also aligns with sustainability at a deeper level. Heating systems in vehicles have traditionally been energy-intensive. By improving thermal efficiency, Tesla reduces total energy consumption over a vehicle's lifetime. When multiplied across global production, the environmental savings become substantial. Lower energy usage means fewer resources required from generation to storage. And inside the cabin, comfort becomes more intelligent as well. Instead of blasting hot air inefficiently, the system carefully balances airflow and temperature control. This precise modulation enhances comfort while conserving energy. The experience feels natural and immediate, reinforcing the idea that sustainability does not require sacrifice. And thermal management is equally important during summer months. While the focus often centers on winter heating, a heat pump system also contributes to efficient cooling. By reversing its operation, the system removes heat from the cabin and battery with optimized energy use. Balanced temperature control ensures that battery longevity is preserved across seasons. And Tesla's approach reflects vertical integration at its best. Rather than sourcing a generic HVAC unit, the company engineered a system specifically for its vehicle platform. This tight integration with battery architecture, power electronics, and software allows for continuous improvements through over-the-air updates. Performance optimization does not end at production. It evolves over time. And as electric mobility becomes the global standard, expectations will continue to rise. Drivers demand vehicles that perform consistently regardless of climate. Governments aim to reduce emissions without compromising reliability. Infrastructure planners seek efficiency at scale. Innovations like Tesla's heat pump address all three simultaneously, by enhancing real-world range, preserving battery health, and minimizing energy waste. And the broader significance lies in mindset. True innovation is not only about creating something new, but about refining every component for maximum impact. The heat pump exemplifies this philosophy. It transforms a fundamental necessity, temperature control, into an opportunity for efficiency gains and system-wide optimization. And it shows that sustainable engineering is not driven by isolated upgrades, but by relentless refinement of every subsystem inside the vehicle. When thermal management becomes intelligent, the entire driving experience becomes more resilient. The heat pump plays a central role in this resilience by adapting continuously to changing conditions, whether the vehicle is parked overnight in freezing temperatures or cruising efficiently across long highway distances. And cold starts are among the most demanding scenarios for any electric vehicle. Battery chemistry reacts more slowly at low temperatures, which can temporarily limit power output and regenerative braking capability. Tesla's thermal system anticipates these challenges. Before the driver even begins a journey, preconditioning strategies can warm the battery pack to its optimal operating range. This preparation enhances performance from the first press of the accelerator, ensuring smooth power delivery without unnecessary energy loss. And the integration between navigation data and thermal management further elevates efficiency. When a route is programmed into the vehicle, the system understands elevation changes, expected speed patterns, and charging stops. Thermal conditioning adjusts accordingly, optimizing battery temperature ahead of high-demand segments or fast-charging sessions. This predictive intelligence transforms what used to be reactive systems into proactive ones. And energy efficiency is often measured in miles per kilowatt-hour, but true efficiency also includes durability and life cycle optimization. Batteries represent a significant portion of an electric vehicle's environmental footprint. By maintaining consistent thermal balance, the heat pump helps reduce long-term degradation. Stable temperatures prevent extreme stress on battery cells, extending usable life and preserving performance over hundreds of thousands of miles. And the ripple effect extends into regenerative braking. When the battery remains within its ideal thermal window, regenerative capacity stays higher even in colder climates. This means more kinetic energy is captured and returned to the pack, rather than being wasted as heat through mechanical braking. Each deceleration becomes another opportunity to reclaim efficiency. And manufacturing philosophy also reflects this commitment to integration. Tesla designs vehicles around centralized thermal systems, rather than layering independent components. The compact packaging of the heat pump contributes to reduce weight and simplified assembly. Weight reduction itself enhances efficiency, creating a reinforcing cycle of optimization. And in urban environments where short trips dominate, efficient cabin heating becomes even more critical. Frequent stops and shorter distances amplify the impact of heating energy draw. The heat pump minimizes this impact, allowing city drivers to maintain strong efficiency ratings, even during winter months. For fleets and ride-sharing services, these incremental savings accumulate rapidly over time. And the system's ability to transfer heat between components also supports performance driving. Under sustained acceleration, motors and power electronics generate significant thermal energy. Instead of relying solely on external cooling loops, the integrated system redistributes heat intelligently, maintaining balanced operating temperatures. This stability allows for consistent power output without abrupt performance limitations. And from a global perspective, adaptability to diverse climates accelerates electric vehicle adoption in regions once considered challenging. Northern Europe, Canada, and high-altitude markets demand reliability under extreme cold. By engineering a heat pump capable of functioning efficiently in these conditions, Tesla reduces geographic limitations on electrification. And beyond performance metrics, there is a psychological dimension to efficiency. Drivers who see stable range estimates during winter gain confidence in electric mobility. Predictability builds trust. Trust drives adoption. When technology works seamlessly without requiring constant adjustments from the user, it removes friction from the transition away from fossil fuels. And software refinement continues to enhance thermal strategies long after delivery. Over-the-air updates improve calibration, optimize refrigerant flow algorithms, and refine predictive conditioning models. This dynamic improvement cycle ensures that vehicles become smarter over time, reinforcing the concept of continuous innovation. And energy sustainability also intersects with renewable integration. As more drivers charge vehicles with solar or wind energy, maximizing how efficiently that energy is used becomes critical. By reducing consumption for climate control, the heat pump ensures that a greater portion of renewable electricity contributes directly to propulsion. And the engineering mindset behind the heat pump reflects a broader transformation within the automotive industry. Efficiency is no longer an afterthought. It is the core design principle. Every subsystem must justify its energy consumption. Every watt must deliver measurable value. And thermal intelligence also enhances comfort personalization. Instead of uniform temperature distribution, airflow and heat allocation adjust dynamically based on occupancy and demand. This targeted approach conserves energy while maintaining an optimal environment for passengers. And looking forward, advancements in refrigerant technology and thermal materials will continue to expand system capabilities. As battery chemistry evolves and energy density increases, thermal precision will remain essential. The heat pump architecture provides a flexible foundation for future enhancements without requiring fundamental redesign. And the future of transportation depends on harmonizing performance, efficiency, and sustainability. By elevating thermal management from a secondary feature to a core innovation, Tesla demonstrates how deep engineering integration unlocks meaningful progress. The heat pump embodies a philosophy that values every increment of improvement, understanding that collective gains redefine what is possible in the electric era. And that philosophy drives a deeper rethinking of how vehicles interact with their environment. A car is no longer an isolated machine consuming energy without awareness. It becomes a responsive system, constantly balancing internal demands with external conditions. The heat pump is a critical link in that balance, translating environmental challenges into opportunities for efficiency gains. And consider the complexity of temperature gradients inside a modern electric vehicle. The battery pack, drive units, power electronics, cabin space, and exterior climate all exist at different thermal states simultaneously. Managing these variables requires coordination at millisecond intervals. Tesla's integrated approach allows heat to flow strategically between these zones, minimizing abrupt changes and preventing energy spikes. And when descending long mountain roads, regenerative braking generates additional thermal energy. Instead of allowing this energy to dissipate entirely, the thermal loop can redistribute portions where needed. During spirited driving, heat from motors can support cabin comfort. During steady cruising, minimal energy input maintains optimal battery conditions. Every scenario becomes part of a coordinated thermal exchange. And this orchestration depends on advanced valve systems and precision-engineered refrigerant pathways. By dynamically altering the direction and intensity of heat transfer, the system adapts without driver intervention. The complexity remains invisible to the user, reinforcing the seamless experience that defines modern electric mobility. And scalability also matters. As production volumes increase across global facilities, efficiency improvements must be repeatable and reliable. The heat pump design supports standardized manufacturing, while maintaining high performance across different vehicle platforms. This consistency ensures that drivers in varying markets receive comparable benefits regardless of region. And in colder climates, the difference becomes particularly noticeable during highway travel. Aerodynamic efficiency may remain high, but sustained cabin heating traditionally consumes significant energy. The heat pump reduces that draw, allowing vehicles to preserve range at cruising speeds. For long-distance travel, this translates into fewer charging stops and greater planning confidence. And the integration with fast-charging infrastructure further amplifies the advantage. When a vehicle approaches a supercharger location, thermal preconditioning ensures the battery is ready to accept high current immediately upon arrival. Efficient heat transfer shortens the time required to reach peak charging speeds. Drivers spend less time waiting and more time moving. And over years of operation, incremental efficiency gains compound. Reduced energy consumption lowers overall electricity costs for owners. For fleet operators managing dozens or hundreds of vehicles, the cumulative savings become substantial. Lower operational costs accelerate the economic shift toward electrification. And the sustainability dimension extends beyond direct energy usage. By maintaining balanced temperatures, the heat pump reduces mechanical stress on battery cells and electronic components. Less stress means fewer replacements, lower material demand, and extended vehicle lifespan. Durability is a cornerstone of environmental responsibility, and even in moderate climates, the benefits remain measurable. Rapid shifts between cool mornings and warm afternoons require flexible thermal management. The reversible operation of the heat pump handles both heating and cooling without redundant systems. This dual functionality reduces component duplication and enhances overall system efficiency. And as vehicles become increasingly connected, data from real-world driving conditions feeds back into engineering refinement. Patterns in climate usage, charging behavior, and performance demands inform continuous updates. The heat pump evolves not only through hardware design, but through software intelligence shaped by global driving data. And the broader energy ecosystem also benefits. During peak winter demand, when residential heating loads strain electrical grids, efficient vehicle heating reduces additional pressure. Each vehicle drawing less power contributes to grid stability. Distributed efficiency becomes a collective advantage. And technological progress often hinges on solving problems that once seemed minor. Cabin heating may appear secondary compared to battery breakthroughs, yet in practice it directly affects range perception and user satisfaction. By addressing this challenge with advanced engineering, Tesla strengthens the overall value proposition of electric vehicles. And thermal optimization also supports autonomous functionality. Sensors, cameras, and computing systems require stable operating temperatures. Integrated thermal management ensures that these components function reliably regardless of external weather. Reliability across subsystems reinforces safety and performance standards. And looking toward future platforms, lessons from the heat pump architecture will influence broader system design. Modular thermal loops, improved refrigerants, and more efficient compressors will continue pushing performance boundaries. The foundation established today allows rapid iteration tomorrow. And electric mobility is defined by precision. Energy storage, power delivery, aerodynamics, and software coordination must align seamlessly. The heat pump embodies this alignment, converting environmental variability into controlled efficiency. By transforming how heat is captured, transferred, and reused, it reinforces a central truth of sustainable engineering. Progress is achieved not only through monumental inventions, but through meticulous optimization of every element within the system.